What are fuel trims? Have you ever seen fuel trim codes stored in an engine control module? Ever wondered what fuel trim values should be? The Engine Control Module, or ECM, controls a closed-loop air-fuel metering system in order to provide the best possible combination of drivability, fuel economy and emission control. The ECM monitors the upstream oxygen sensor signals and fine-tunes the fuel delivery based on this signal once the engine has entered closed-loop mode. When an engine's oxygen sensors are cold, most ECMs will enter an open-loop mode. In this mode, the control loop is not a complete cycle, as the ECM does not react to oxygen sensor feedback. Instead, the ECM makes decisions based on pre-programmed information and various other sensor inputs. Once the oxygen sensors have reached operating temperature, reliable signal information can now be processed by the ECM. The ECM will now enter closed-loop mode. This is known as feedback. Changes made to the fuel delivery system based on this feedback affect the long and short-term fuel trim values. Short-term fuel trim values change rapidly in response to the upstream oxygen sensor feedback or signal. The long-term fuel trim makes course adjustments to recenter and restore control to short-term fuel trims. The ideal long-term fuel trim values should be around 0, while normal short-term trims can range between -3 to +3. A positive fuel trim value indicates that the ECM is adding fuel in order to compensate for a lean condition. A negative fuel trim value indicates that the ECM is reducing the amount of fuel in order to compensate for a rich condition. Here's a practical example. I have an oscilloscope connected to an oxygen sensor signal. Watch what happens when I introduce an air leak. The oxygen sensor signal reacts when the exhaust from the lean air-fuel mixture reaches the sensor assembly. With the second oscilloscope channel connected to the fuel injector trigger signal, watch what happens to the pulse width when I introduce the same air leak. You'll notice that the O2 sensor reacts to the leak a moment before the injector pulse width increases. If we keep watching the O2 sensor signal, we can see the pattern returns to normal after a few seconds. The mixture has returned to a stoichiometric value, and yet we still have the air leak. To explain how this works, we'll need to look at the vehicle's fuel trim data. You'll notice that shortly after the air leak is introduced, the short-term fuel trim changes to a positive value. This means the ECM is responding to changes in the mixture as a result of the upstream oxygen sensor feedback. The greater the air leak, the higher the positive value of the short-term fuel trim. The higher the trim value, the longer the injector pulse width. Now, let's monitor the same signals while this time introducing a rich mixture. By opening the EVAP purge solenoid, a rich mixture is introduced to the intake manifold and therefore affects combustion. We see the effect on the upstream O2 sensor first. Next, you will see the short-term fuel trim move to a negative value. There will be a time delay before there is any reaction at the injector, while the ECM decides whether this is a trend or a momentary change. This can be seen on the oscilloscope as the injector pulse width is now reduced. These trims can often be referred to as adaptive strategies, meaning the ECM can learn or adapt to minor problems or wear without sacrificing engine output. Short-term fuel trims are temporary only. Once the ignition is switched off, they reset to 0. Long-term fuel trims are set based on the activity of the short-term trims. If the short-term fuel trim values meet the requirements of the engine during differing operating conditions, the long-term trims will not change. If the short-term trims operate outside these normal parameters for a predetermined time, then the long-term values will change. These changes are written to the ECM memory and can be utilised for fuel correction in open loop. By continuously monitoring the total amount of fuel trim, both short and long, the ECM is able to effectively control the air-fuel ratio. There are limits to the amount of fuel trim correction that can be made. If these limits are exceeded, a fuel trim DTC will be set. Pre-combustion faults are poor fuel quality, lower or higher than normal fuel pressure, restricted fuel flow, slow injector opening or closing times, blocked or partially blocked injectors, dribbling injectors, intake air leaks or unmetered air entering the intake system, leaking or incorrectly operating evaporative emission systems, incorrect air mass or manifold absolute pressure readings, and leaking EGR valves. Faults during combustion may include low compression, no compression, ignition fault causing misfire or inadequate combustion, poor cylinder turbulence causing incomplete combustion. Post-combustion faults may include any leak before the upstream oxygen sensor that allows air into the system, an oxygen sensor with poor signal outputs, use of non-sensor safe sealants, a contaminated oxygen sensor, or a restricted catalyst. Monitoring fuel trim data when looking for faults makes perfect sense. These parameters can be found in the OBD section of most scan tools. This makes diagnosing a misfire on a multi-cylinder engine relatively easy. Once you have performed a repair where the fault may have altered the fuel trims, it's best to use a scan tool to reset these values. Some of these repairs may include cam belt replacement, cylinder head R&R, vacuum leaks, exhaust leaks, oxygen sensor replacement, or any condition that may have caused dilution of the engine oil. It's also best practice to reset fuel trims after something as minor as an oil change. After any repair, long-term trims will eventually reset and adapt to new conditions. For customer satisfaction, always reset fuel trims as part of the repair. Understanding how fuel trims operate is relatively straightforward, but it's an essential part of any diagnostic process. Thanks for watching. See you next time.